Good day everyone, my name is Marohnic and today I'm going to present you a research topic, estimation of materials parameters of strain life fatigue behavior using empirical and artificial neural networks based approach. Estimation of fatigue lives and material behavior along with determination of corresponding material parameters is usually needed in early design stages that precede experimental testing. However, experimental testing and characterization of material behavior is the most accurate, but also time-consuming and resource-consuming. There is the reason why a number of estimation methods are developed from the mid-20th century that try to link monotonic properties from easily obtainable monotonic experiments and cyclic experiments, cyclic and fatigue material properties. So in this paper, I'm going to present to you methods for estimation of fatigue, Baskin-Coffin, Manson parameters that we saw on previous slide. So fatigue strength coefficient, fatigue strength exponent, fatigue ductility coefficient, and fatigue ductility exponent. This is the list of commonly mentioned and used fatigue parameters estimation methods. We also call them empirical methods, and from this table we can see that most of them are proposed for all metallic materials together or all steels together. Only a uniform material law treats unalloyed steels and low alloy steels separately from aluminium and titanium alloys. We can also see from the list of monotonic properties used for estimation of certain coefficient or exponents that most of these methods assign constant values to exponents B and C, which is quite wrong because different material groups have different values of average of these coefficients. So I mentioned two drawbacks of existing methods, but I will mention two more. First is that they are developed on a small number of data sets, some even only on 16 data sets, which is really low, and there is no prior statistical analysis for identification of relevant monotonic properties. So we suggested a new approach that takes into consideration all these four issues. I must emphasize that fatigue parameters estimation as well as cyclic parameters estimation on the basis of monotonic properties is a function approximation problem, so it's a regression problem, and one of the keys to successful regression analysis is identifying suitable subsets of potentially used predictors that will be included in the final regression model. New approach, the flow is represented on this slide. So first a large number of experimental data were collected and those data are curated, so we have only quality data. Steels were grouped according to the alloying element content into unalloyed, low alloy and high alloy steels, and statistically significant differences were established among these groups. We developed a detailed procedure for identification of appropriate subset of predictor variables and determined relevant monotonic properties for estimation of each parameter and each steel subgroup, and developed artificial neural networks for estimation of strain life parameters. Obtained networks were evaluated on an independent set of data, and results were compared to empirical methods and experimental values. For this research, materials data were collected from relevant literature through MADAT Materials Properties Database, and here you can see criteria that we used. These are high quality data. We used only strain controlled, fully reversed axial cyclic tests, materials that were tested at more than 4 different strain amplitudes and at range of strain amplitudes more than 0.4%. Experiments were performed in air at room temperature, and for statistical analysis and development of artificial neural networks, 116 experimental datasets were used, and additional 49 experimental datasets are used for unbiased evaluation of both artificial neural networks and empirical methods. Here you can see overview of monotonic properties that were established as relevant for estimation of fatigue parameters. For some coefficients, for some parameters, analysis could not be performed, so later on we used most commonly available monotonic properties, tensile strength, yield strength, and reduction of area for development of neural networks. We took monotonic properties determined on previous slide, developed neural networks, outputs from neural networks were strain life parameters, and then we calculated strain life behavior. As far as artificial neural networks development, so a series of networks were developed, but 12 best were chosen for estimation of each strain life parameter of each steel subgroup. Type of network used was two-layer multi-layer perceptrons with hyperbolic tangent transfer function in hidden layer and linear transfer function in the output layer, since this kind of network approximates any function arbitrarily well. Error function was mean square error, and growth method is used in order to determine proper network architecture. So networks were trained from one neuron in hidden layer to upper limit. Upper limit was determined depending on number of inputs and outputs, taking into account that training examples are enough for solving all training equations. We implemented methods for improving generalization, so early stopping or regularization depending on algorithm used. We implemented k-fold cross-validation for maximization of available data, since those numbers you saw on previous slides are not that large when talking from ANN perspective, but are quite a lot when talking from materials testing. K-fold cross-validation helps to maximize learning from limited number of data, and we used for performance ensemble of networks, because several networks usually perform better on unseen data than one network. Evaluations were performed on unseen data, so unseen data are those not used on for development of ANNs. We compared performance with commonly used estimation methods, so UML, modified 4-point correlation method, hardness method, and medians method. For strain life parameters evaluation, we calculated percentage of values estimated by selected methods of artificial neural networks that deviate up to 10, 12, and 30% from experiment-based values, but also for for estimation methods. We obtained following. So for estimation of fatigue strength coefficient, artificial neural networks are better or equally good for all three subgroups. Especially for high alloy steels, this is more pronounced because ANNs perform much better. As far as fatigue strength exponent B, ANNs perform much better for all three groups, especially high alloy steels. Again, if we remember, most of the empirical methods assign constant values to exponents B and C, so this is most probably the cause. For fatigue ductility coefficient, the results are better than empirical methods, but not as successful. This is because no statistically significant monotonic properties were determined for unalloyed and low alloy steels. High alloy steels are a special kind of problem because they usually contain materials that are very diverse in behavior, in parameters and everything. Okay. For fatigue ductility exponent C, neural networks are slightly better or equally good as conventional methods, up to 15%, I think, is the performance better for low alloy steels in these up to 10, up to 20% deviation than empirical methods. It is not enough to evaluate only parameters. It is very useful to evaluate also strain life behavior. For this we used conventional error criterion. We calculated fraction of data points within predefined scatter bands. We did this not for steel subgroups, but rather for one material. So we had 6 datasets of 4140 steel, 42 chromium, molybdenum 4 steel, so low alloy steel. We calculated number of load reversals for 8 strain range amplitudes, and this is the result. So we can see that neural networks in general perform slightly better in these smaller scatter bands or equally good as empirical methods. But these are actually averaged results, because when we take one data set and draw strain life curves, we see that with parameters estimated with artificial neural networks, we obtained really good approximation of real strain life curve, and deviation from the experimental curve are more pronounced for conventional methods. Conclusion can be given that ANNs are a promising tool for estimation of material strain life parameters and behavior of metallic materials. Our planned research activities include more detailed evaluation using some additional criteria, investigation of possibility of using additional parameters for improving estimation, and application of other machine learning methods. This research has been supported by Croatian Science Foundation and University of Rijeka. Thank you for your attention.